Hello everyone, my name is Maja and I work at Facebook on data infrastructure for iterative and graph processing team. Sorry? Okay, sorry. Should I go again? My name is Maja and I work at Facebook on a team for data infrastructure for iterative and graph processing. And today I'm going to talk about one of our applications, collaborative filtering, or how to do large-scale item recommendations using Apache Giraph. This is a joint work with Alexander Illich, who is also here today, so if you have questions later, you can ask either me or him. Okay, so what I'm going to talk about, I'm first going to introduce collaborative filtering and talk about motivation and challenges that we have with it at Facebook. Next, I'm going to talk about Apache Giraph, which is a platform we used for doing collaborative filtering. I'm going to go deeply into how it is how we can distribute it, mainly how common approaches do it, and then our novel approach for distributing it. I'm going to talk about some additional features, like how we can use social signals there, and how we apply the results from collaborative filtering at Facebook, and conclude in the end. So, as probably everybody here knows, collaborative filtering are techniques for predicting users' interests based on interests of many other users. And the problem became very popular with Netflix prize competitions years ago, where the objective was to predict user movie ratings, but it can be applied on many other fields. So for example, on Facebook, we might want to recommend pages to people. And a simple example would be, say I like Disney roller coasters, Disneyland and Six Flags, and Alexander likes only Disney and roller coasters. Just based on this information, it seems that me and him have similar interests, and he might also be interested in the other two pages, and he can get these recommendations on Facebook. So collaborative filtering algorithms, they start from some known user-to-item ratings, and then they try to predict how a user would like other items from the data set. And the way this is often approached is with matrix factorization. Here we present all the known user and item ratings as a very sparse matrix. And what we want is to predict the missing values inside of the matrix. And the way to do this is to present each user and each item as a feature vector. And the objective for these feature vectors is that their inner products closely match the known values inside of the matrix. The assumption is that after you closely match the known values, the missing values can be well approximated by the inner products as well. And this is the basic form of what the objective function looks like. Here, R are the known user item ratings from the input, and X and Y are user and item feature vectors we are trying to find. So here you can see that we are trying to minimize the difference between known and predicted rating. And the second part is just the regularization, which prevents us from overfitting and getting numerical problems and stuff. So it is impossible to find, well, it's infeasible to find the exact solution for the above formula, but there are two iterative approaches that slowly converge towards a solution. First one is stochastic gradient descent. Here you iterate through all the known ratings and move both user and item feature vectors slightly in the direction opposite of gradient to always go closer and closer to the solution. The second one is alternating least squares. There you first update the user feature vectors while keeping the item feature vectors fixed. Then you switch between users and items and keep iterating that way. And the main challenges for us here, as with many other problems that we face at Facebook, is our scale. So a typical data set for collaborative filtering for us consists of hundreds of billions of user item pairs. We have over a billion users and tens of millions of items. And kind of related to that is performance. As everybody, we want to train models and iterate quickly on them and to be able to use more features. And like the current solutions in this field talk about 2 orders of magnitude less of data. And I'll talk later why the current approaches are not going to scale to what we need. And this is just to show that here is the graph of how RMSE changes with different number of features. So here we can see that with more features we can get better quality of results, which again explains why we need to be as performant as possible. Okay, so our platform of choice for this algorithm was Apache Giraph, because we've been working on it for about 3 years, and we know it scales and performs well on the data sets that we have. I'm going to give you a brief introduction of what it is if you didn't hear about it before. Apache Giraph is an open source project. It is a distributed platform for doing iterative and graph processing on massive data sets. For us at Facebook, this means over 1 billion vertices and up to 1 trillion connections. And just to give you an idea of how it performs, you can do an iteration of PageRank on graph this big in about 2 minutes on a cluster. Giraph operates on graphs, and it provides primitives which are vertex IDs and values, as well as edges and values associated to them. A simple example would be vertices could be Facebook users, vertex values maybe their favorite machine learning algorithm, edges are friendships on Facebook, and edge values the strengths of these friendships. Giraph runs on top of Hadoop, but it uses Hadoop just as a resource scheduler and manager. Giraph jobs are map-only jobs, and the way they go is that in the beginning you read data, and then you keep data in memory, allowing you to iterate through it as many times as you'd like. Mappers communicate directly through network to allow this. So even though we run on top of Hadoop, we don't have the inefficiencies of MapReduce, where you need to read and write data from the disk in between each 2 iterations. And the basic overview of Giraph workflow is you have a set of machines that you want to run your job on, and your graph gets automatically distributed across these machines. After your graph is loaded, the computation starts. It consists of a certain number of iterations, which we call supersteps, and in each superstep, each vertex does some kind of local processing. So it can modify its value, modify its edges, and it can send messages to other vertices in a graph. After every vertex has done its computation, there is a global barrier, which ensures that all the messages have been delivered, and then the next superstep starts. And in the next superstep, vertices again do some kind of local updates, and they can consume the messages they received from the previous iteration. They can send new messages and so on. This is just like a basic overview. We have a lot of additional features that allow for different algorithms, some things for global computation and so on. Okay, let's go now back to the collaborative filtering and talk about how we can distribute this problem. So a common approach to distributing it in a system that has similar architecture as Giraph has is to look at the problem as a bipartite graph. So you have 2 types of vertices, users and items, and edges represent the known ratings. So in order to do an iteration of either stochastic gradient descent or alternating least squares, what you do is you send the feature vectors for users or items through the edges of this graph. Now there are a few problems with this solution. First, the data sent per iteration is very large. So you need to send, since you are sending the feature vectors through each of the edges here, the amount of network traffic that you have is number of known ratings times number of features. So if you think about having 100 billion ratings and say 100 features, the network traffic to do a single iteration would be about 80 terabytes, which is a lot, of course. The second problem is memory. You need to be able to store all these messages in memory, so the memory requirements are about the same here. Large degree items represent the memory and processing bottlenecks because they need to be able to hold all their user features and process them. And finally, the modification in stochastic gradient descent are not exactly equal as in sequential solution because you don't always work on the latest value, but you kind of send a copy of feature vectors in the beginning of the iteration instead of updating the latest one always. So in order to overcome all these issues, we came up with like a different data layout for distributing the collaborative filtering. And in our solution, users are still vertices, but items are part of what we call a worker data that is like a local data on each of the machines. And I'm going to show you how that looks now. So you again have your set of machines, and users are loaded as vertices, but items are now stored in worker data. And in order to do a single iteration of one of these algorithms, what you need to do is to have each user and item pair available on the same machine at some point of time in order to be able to update that pair. So to make that available, we put workers in a circle, and we're going to be rotating the item sets across the lines of this circle in a way that each item set is going to visit each machine exactly once after a number of machines sub-iterations. Now let's look at the problems we had before. So the amount of network traffic doesn't depend on number of ratings anymore. It doesn't even depend on the number of users. It only depends on the number of items you have, number of features, and number of machines that you use for your job. Memory requirements, since they were related to network traffic, are also lower now. Skewed item degrees, items with large degree don't represent a problem anymore, because items never hold information about what are their users. This information is always stored on the user side. And updates in stochastic gradient descent are exactly equal as in sequential solution, because we never have a copy of feature vector for neither users or items. We always have just one value which we are updating. Okay, so how does this perform? To do the comparison, we used the numbers that were published for Spark MLlib solution. So Spark is one of the leading open source implementations in this field, and they have implementation of what I called common approach here. The experiments here were conducted on scaled copies of Amazon Reviews dataset, which originally contains 10 million ratings. So you can see in this graph that we are order of magnitude faster. The rotational approach is order of magnitude faster. Additionally, what was the most important thing for us, we can handle over 100 billion ratings, while the largest number here reported was about 3.5 billion. So you may wonder, is common approach always worse than rotational approach in terms of network traffic? And the answer is no. So we can look at this from the point of view of each item, and based on the item's degree, see which of these two approaches would be better for it. So in common approach, in order to do an update for an item, the amount of network traffic that you have is number of features times item degree, because you send the feature vector through all the item ratings. In rotational stochastic gradient descent, it is number of features times number of workers, because you're rotating the item feature vector across all your machines. And in rotational alternating least squares implementation, it is number of features squared times number of workers, because there you need to keep a matrix for each of the items. So you can see, let's say that we have 10 machines that we use for our job, and we have 100 features, then the limit for item degree for stochastic gradient descent would be 10, and in alternating least squares it would be 1,000, so all the items with more than 1,000 are better to go with rotational approach, and items with less than 1,000 are better to go with the common approach. So we implemented this hybrid solution to prevent the slow degree items from small degree items from slowing us down. Okay, and I'm going to give you a few additional extensions here that we implemented for improving the performance as well as the quality of results. So first, you might have noticed that we only use the number of workers connections to transfer the data in the solution which I proposed. And in practice, the slowest of these connections were actually causing the bottleneck in our algorithm. And we knew that we need to use all the connections between the machines in order to overcome this problem. And even though it might sound simple, finding the pattern by which we want to transfer the items was actually an interesting problem. So the first step was an obvious one, to split each item set on each worker to number of workers minus 1 sets. And then what we know is that each of these small subsets need to go for different network connection here. Now this problem is actually equivalent to finding, to decomposing a complete graph into edge disjoint Hamiltonian cycles. And construction for the scheme by which you go here uses Latin squares and is only possible for the odd number of machines. The second one one is related to the quality of results. So since we are Facebook and we have a lot of information about your social connections, probably even more than your interests, we wanted to use this information as well as like on top of the user to item ratings in order to get better quality of recommendations. And we looked into a few approaches here, and we decided to go with social regularization. So we additionally add the objective of users' latent features should be similar to his or her friends. So here we have a bit more complex formula. We added user and item biases, and you can see like this first part is what we had before. We are trying to minimize the difference between known and predicted ratings. The second part is the standard regularization, and then the third part is the social regularization. Here you can see that we are trying to minimize the difference between user and his friends feature vectors with optional coefficients on friendships to specify that some friendship is stronger than the other. And the parameter alpha here allows you to play with how strong you want to have the social signals. This extension is easy to add in Giraph model because we already have a notion of vertices and edges and messages sent between them. So we just have like edges or friendships between people, and we are going to be sending the user feature vectors to their friends through messaging model in Giraph. Additional complexity for this is number of friendships times number of features, because you are sending each feature vector across each friendship. And apart from generally improving the quality of results, this helps solve cold start problem. Collaborative filtering often suffer, I mean, most of them, they can't give good predictions for users who don't have a lot of ratings, who don't have a lot of information about their interest. And by using their social signals, we can actually still get pretty good recommendations for them from these algorithms. And then there are a lot of additional features here that we have, like we can track RMSE, average rank, and area under the curve for during each iteration, so you can know how your training is progressing and whether you should change some parameters. We have a way to combine stochastic gradient descent and alternating least squares, since they operate in the same objective function. This is possible to do, and it proved to improve the RMSE on some data sets. We have implementation of different objective functions. So when we have implicit feedback instead of explicit user feedback, there are some different functions you can use there. Degree-based regularization in order to work better with skewed item degrees. Incremental training means just that we can continue from the previous model and improve on it instead of starting fresh. And we have implementation of fast top carry recommendations on top of all of this. And this is another approach to collaborative filtering you can take, so a bit simpler than matrix factorization. This one is based on neighborhood models, and here the algorithm starts by calculating the similarities between items. The similarity between items is defined by looking at the overlap of users for two items and looking at some global item properties. So one simple thing here, like if you look at these two items, their similarity could just be 3 because they have 3 common users. You can normalize that by the item degrees. You can use like cosine similarity, Pearson similarity, or something like that. And we have actually like easily adjustable formulas for all these calculation parts in order to allow easy experimentation. After you get the item similarities, you can also get the user recommendations by looking at all the items for a user, and then all most similar items for each of the user's items. And we used to have this implementation in Hive, and then we implemented it in Giraph, and it was about 10x faster and was able to handle much larger data sets. And finally, how do we apply the results from collaborative filtering? So first, the feature vectors that you calculated from matrix factorization, you can directly add them to your ranking models. For example, this is what we did in Instagram, where we try to predict, where we try to recommend the accounts to follow to people. You can get the user to item score in real time. So for example, if you have recommendations coming from a few sources and you need to be able to sort them in some way in order to show just top 2 or 3 recommendations to the user, you can use this to actually sort that list. Then direct user recommendations, which you can get either from matrix factorization or from the neighborhood-based one, that you can use as additional candidate source for any of these algorithms. And lastly, context-based recommendations. That means like from item similarity, one, you can get, when user is within some context, you want to show him recommendations related to that context. So for example, if user liked the page or viewed the video, you want to show him what to do next, like what to look at next. So to conclude, I presented here a scalable implementation of collaborative filtering on top of Apache Giraph. It is highly performant. It can handle hundreds of billions of ratings. And I talked about how we utilize social signals, for example, and how we calculate item similarities. And proving its value, these approaches have multiple use cases at Facebook. So thank you. Here are 2 URLs. The first one is our blog post about the matrix factorization, and the second one is a link to paper about Giraph on VLDB this year. So if you're interested, you can go check them out.